So we had, what were the names of the three primary types of radioactive particles we talked about?
Alpha,
Beta, gamma.
Alpha, beta, gamma. And so this here is summarizing alphas. I know you could read it there, but what can you remember without reading?
Protons.
They're positive. They're 2 protons and 2 neutrons. How easy are they to stop?
Very.
Very easy. It doesn't take much shielding at all for alpha radiation to be stopped. But there's a different side of the coin there. You guys know about radon gas? Anyone? Jackie kind of nodded her head. Anyone got a firm understanding there? Well, is radon gas good or bad? Bad. Okay, so we understand that. Where do you find radon gas? Where? Jackie?
I said somewhere bad.
Somewhere bad. You tend to find it in your basement. Now, if we look at the table back there, radon gas is the bottom red one. As you go down, what's happening to the mass of the nuclei?
It's heavier.
Getting heavier. So radon gas is very heavy. If it's in the gas form, the volume taken by a number of molecules is the same, whether it's oxygen or radon, takes up the same volume. But if radon is much more massive than oxygen, what does that tell you about its density? It's a much higher density. And so our air, here's something you don't know, or maybe you don't know. What is our air made up of? 79% nitrogen. Excellent. 79% nitrogen and about 20 to 21% oxygen. Nitrogen and oxygen have very similar densities that are far, far less than the density of radon. So what's radon gas going to do in oxygen and nitrogen gas?
Sink to the bottom.
Sink to the bottom because of the densities. Right, so we can think these things through. That means radon gas is going to be found down lower. Radon gas is part of the decay sequence of uranium. So anywhere that you have naturally occurring rock, you're going to have some naturally occurring uranium in that rock. Some places have more uranium in the rock than others. And if you have that uranium in the rock, it's going to be going through a decay and periodically producing helium and much more rarely producing radon. That radon gas, in and of itself, isn't very dangerous. But you breathe it in, and you get it in your lungs. Well, actually, what actually happens is the radon gas, the danger is it decays on like a piece of dust, and then you breathe in that dust, and the decay for the polonium that's produced after the radon gas, it produces a lot of energy, and it can cause damage to tissues. And so since it's a gas, you can breathe it in. And if it decays in your lungs, you know with 100% certainty that energy is going to be absorbed by your lungs because it's going to be absorbed by the first thing it hits. If it's in your lungs, that's your lungs. And that's the real danger with radon gas. The energy produced by the radioactive decay of polonium, if that is absorbed in your lungs, then you do damage to your lungs. And so that's why we try to limit the amount of radon gas in our house basements. We don't worry about the radon gas in the attic because it's going to sink from there. But we worry about it in the basement because of the danger there. The same thing, I talked about radioactive things. I used bananas and milk as examples of things that are radioactive. If I have a banana sitting on my hand, just geometrically, no more than half of the radiation emits could ever go into my hand. The other half would go somewhere else, right? But if I eat that banana, it's all going to be absorbed inside my body. So when you eat something radioactive, it's more dangerous than having something radioactive outside. And if it's an alpha emitter, it's much more dangerous than if it's a beta emitter because you have more energy that's going to be absorbed. So alphas are easy to stop, but if you eat an alpha emitter, then that's more dangerous than others because you know it's going to be stopped by your body. But if something's outside and it's alpha emitter, we don't have to worry because at the very worst, if something's outside your body as alpha emitter, it'll be absorbed by your skin. Right? That's not going to cause you great harm. Okay. Next one, betas. Okay, before you can read them, tell me about beta particles. They're negative charge. What are they like? They're like electrons because they are electrons, but there's no electrons in the nucleus, remember? So it's a conundrum. You actually have, when I was in high school, my teachers were teaching me about this. I just thought, that's easy. A neutron is an electron and a proton bound together. But that's 100% wrong. Right? As you saw from your homework that you turned in yesterday, what is a proton? It's made up of three. We can see that from the picture in back. What are those three things called? Quarks. So a proton is equal to 3 quarks. It's an up, up, down. And a neutron is likewise 3 quarks, but it's an up, down, down. Ups and downs, these quarks, they're not the same thing as electrons. So there's no electrons in there. What has to happen to make a neutron decay? You have a neutron that will spontaneously become a proton plus an electron antineutrino. So that's the way we draw the equation for what happens. But what really has to happen is something has to, you have an anti-up and the up combine, annihilate, and they're going to produce, along the way, if they produce a down and an anti-down, then this down can come in here. Right? It's a complicated process. You don't have to know that process at all. I'm only saying this to illustrate that there are no electrons in the nucleus, but the nucleus creates electrons. But it doesn't create charge. Because in this process, what's the charge inside that box? Neutral. It's neutral. We started with 0 charge, we end with 0 charge. But it created a proton, it created an electron as it decayed. Okay, electrons. How easy are electrons to stop? They're the ones that are intermediate. So to stop an electron, if you have, like a piece of aluminum or lead, you'll probably do a pretty good chance of stopping an electron. So things about the electrons here penetrate fairly deeply into the skin. And remember last time I had a picture here of the penetration depth, the energy deposition is a function of depth, and talked about how this is used to treat cancerous tumors. The goal in treating cancer is to kill the cancer. The radiation is designed to kill the cancer. It's going to kill some other cells in the body. That's an unavoidable byproduct. And remember, using protons, because protons are more massive, they'll deliver a higher percentage of their energy at the end point, so you can have less damage to intermediate material. What else do they do for people who have cancer? Instead of taking electron or proton beam therapy, what else would they do for therapy? Okay, well, that's what I was talking about, was radiation. Chemotherapy. What is the goal of chemotherapy? It's to kill cells. And so you're taking chemicals that are designed to kill, hopefully, more cancer cells than other cells. But the chemicals you take in chemotherapy, they kill rapidly reproducing cells because cancer cells are rapidly reproducing. But so are your hair follicles. And so you end up killing hair follicles, hair falls out, right? Because the same thing that's killing the cancer is also killing the hair. Fortunately, it grows back for some people. If it would grow back for everybody, I might take chemo just to, regenerate. So, beta particles, finally, gamma particles. Gamma particles are light. They're the same thing as light. They're electromagnetic waves. And those things are really hard to stop. So that's where you need the really significant shielding to stop gamma radiation. It's the most penetrating of all. It's no charge because it's a particle of light. Okay, so what holds the nucleus of an atom together? What it is this strong nuclear force. Remember, we had the two forces that we've dealt with a lot in physics. We had the gravitational force and we had the electromagnetic force. There are two forces that work in the nucleus to actually hold together, the strong and weak nuclear forces. Our textbook just talks about the strong nuclear force. But what's unique about it is it's a very short range force. So we have two pictures here to illustrate the range. If we have two, let's say protons, positive charge, and they're really close to each other, you're going to have a significant repulsive force because like charges repel. But you're also going to have a significant strong nuclear force that's attractive, holding them together. If you separate them by a little bit, if you just did so little as separate it by one neutron, so if you had one neutron here and then you had the positive and the positive on either side, then the repulsive force would still be significant, but the attractive force would be non-existent. So what we have is a long-range force for the repulsion, a short-range force for the attraction. That makes some problems as we put atoms together. If we make a helium atom, okay, you don't have to answer these questions because, I don't even have it set up, so don't worry about trying to. Strong force is the force that holds the electrons in orbit? Nope. It doesn't even affect electrons. The strong force only affects protons and neutrons, nothing else. Nucleus that holds, it's a force in the nucleus that holds nucleons together. That's the correct answer. Okay, so moving on. If we have the helium atom has 2 protons and 2 neutrons. You might ask, why doesn't it have just 2 protons and no neutrons? If it had 2 protons and no neutrons, it'd still be helium, right? Because it has the same number of protons in the nucleus. But it's not stable because the repulsive force between the 2 positive charges would push the 2 protons away from each other. So in order to hold them together, we have to push the 2 positive charges farther away, which makes that repulsive force a little weaker, and put a neutral charge in there so that it's not repulsive, but it's still attractive. And so the helium nucleus, the helium-4, our most common nucleus, has 2 protons and 2 neutrons, and we have attraction between all 4 of them from the strong nuclear force. And then we have repulsion just between the 2 positives. And in this case, we have more attractive force than we have repulsive force, and it stays together. If you take away one of the neutrons, that would be helium-3 because it has 2 protons and 1 neutron. It's still stable. It still has more attraction than repulsion. But if you were to take away the last neutron, it would break apart. Now, if we get to a bigger nucleus, let's take something like uranium. I think uranium is what I have here. Well, it doesn't say the name. You get more positive charge. The repulsive force just builds up bigger and bigger and bigger. So you have to throw a lot more neutrons in there to counter that. So if you look at that graph there behind Alex, you see down here at the bottom, the white is the stable nuclei. And as you go up here at the bottom, you have just about the same number of protons as you have neutrons. So the vertical axis is Z, that's the atomic number, the number of protons. Horizontal axis and the number of neutrons. This is the slope of 1 up to about here, but then it starts curving, and it keeps curving. So you have to throw in more and more neutrons as you get more protons to give more attraction and push them apart to decrease the repulsion. So that's why when you get to something like the uranium, you have, 146 neutrons and 92 protons. Way more neutrons than protons because you need to space out the positive charge and put in the neutrons that will help hold it together by the strong nuclear force. Now, half-life and transmutation. I've talked about transmutation. Remember I talked about alchemy changing from one element type to another? Half-life is not just the name of a game. Actually, these days, the game's so old, you guys probably haven't played it, right, everyone? Okay, Eric's like, yeah. What's the symbol for the Half-Life game?
Oh, boy. Isn't it if I remember correctly, it's like a little running man or circle, isn't it? Kind of.
I thought it was this.
Yeah.
Okay, and that's because that's a symbol we use for actually the decay constant in radioactive materials. With radioactive nuclei, and I've talked about this a number of times, it's like having my stylus balanced It's balanced, right? But it's not very stable. Just a little bit of me hitting this and it's falling over, right? I don't want it to fall over, so I'm taking it back. We can't predict when it's going to happen, but we can predict in an atom in the nucleus. We can say, well, every second there's this percentage chance that it will decay. And so we have a probability problem. There's a probability of decay each second. And so we can calculate the time, and there's a certain time when the probability of decay is 50%. And so we call the time when the probability of decay is 50% the half-life. And nobody here, actually one person is taking calculus. Yeah. Oh, wow, lots of people. Oh, and Alex too. There's a lot more people with calculus than I anticipated.
Can't tell you anything though. It was years ago. True. Yeah, I took it. I took it in high school.
Okay, this is the fundamental equation that tells you about the radioactive decay. dN, I forgot dt. dN dt, the rate that they're going to decay, n is the number of radioactive nuclei, t is time. D is, for everyone who doesn't know calculus, just don't worry about it. dN dt is minus lambda n. Well, if you want to solve this equation, you do what we call separate variables. You multiply everything by dt to get dt away from n, divided by n to get n away from dt, and you end up with dn over n is equal to minus lambda dt. This lambda is why half-life has lambda as its logo. Then you integrate both sides, and you have natural log of n over n initial is equal to minus lambda t, or we can say the number of radioactive nuclei at any moment is equal to the number we started with, e to the minus lambda t. Now, you are not responsible to know any of the math I just did. I did it because there was a significant fraction here that actually is taking calculus and can understand it. If you can understand it, then it makes more sense. If you can't understand it, well, don't worry. So the number of radioactive nuclei that remain depends on the time. And at the time that we call the half-life, how many will remain? Half, right? That's the definition of the half-life. So different elements have different probabilities of decay and thus different half-lives. So let's think about this logically. A certain isotope has a half-life of 1 day. This means the amount of isotope remaining at the end of 2 days will be, at 1 day, how much would remain? Half. After 2 days, okay, we have 0 or a quarter. The way statistics works is after 1 day, half of them will have decayed, leaving 1/2. So the start of day 2, how many do you start with? 1/2. And during that day, half of them will decay. So you're left with 1/4. So if you go the third day, you start with a quarter. During that day, half of that 1/4 will decay, leaving you 1/8. And so you have less and less as time goes on, because the probability of decay remains the same, but every time one's decayed, well, the number you have remaining is smaller. So this is what a graph looks like of that. This is what we're going to be simulating today by using dice. Now, I have to tell you, dice are not statistically significant when you only have 25 of them. To be statistically significant, we need to have like 1 million dice. But who's going to sit there and count, okay, we have this many ones out of 1 million dice? No one, right? Furthermore, where are we going to get 1 million dice? Where are we going to roll 1 million dice? There's many logistical problems. In reality, if I have a radioactive sample, it has many more than millions of nuclei. And so the statistics are reasonably strong with radioactive decay when you have a sample. But they're still not perfect because you're dealing with statistics. So the reason I'm not having everybody use the same set of numbers in today's experiment is so you can see the variation, that it's not the same every time because of statistics. Now, the last thing before we get started, actually not the last thing, but pretty close, talking about actual examples of radioactive decay. We've talked just briefly about carbon-14 dating. And the textbook says that carbon-14 is created in the atmosphere. Here is how it's created. The atmosphere is 79% nitrogen. Lots of nitrogen up there. When a neutron from the sun hits a nitrogen, it can be absorbed. And so there's something not shown here. A nitrogen 10N. What does the superscript of 1 mean? Or not nitrogen, a neutron. What's superscript of 1 mean? 1 what? Means one thing in the nucleus. A subscript of 0 means what? 0 protons in the nucleus. So you can take those two numbers. There's one thing in the nucleus, but 0 protons. What's left? Neutron. So that's how we write a neutron when we're doing, nuclear math. 14,7N, that means we have 7 protons in the nucleus, 14 things in the nucleus, so 14 neutrons. Add those together and it gives us that little star means it's unstable. For the briefest of time, we have this nitrogen 15, but it quickly decays into and they put H, so I will keep it the same. Yeah, that works for me. Decays into that. How many electrons do you suppose are with that proton that came out? 0. It's not going to have any electrons. So this is going to have a negative charge. But this one here, you started with 7 electrons with your nitrogen. With the decay, it's still going to have those 7. Whoops, I did this backwards. It's still going to have those 7 electrons, so it has 1 extra electron. So the carbon will initially be negative. The proton's initially positive. That proton's going to pick up an electron and be neutral. The carbon's going to shuck an electron to get back to being neutral. So that's the reaction that occurs in the atmosphere that creates carbon-14 in the atmosphere. With radiometric dating, with carbon-14 dating, what we do is we say, okay, we started with this much carbon-14 compared to this much carbon-12. And if we started with this ratio, we measure in something that has stopped exchanging air with the atmosphere, right? As long as I'm alive, I am eating plants. Some people eat animals, but those animals ate plants. And the plants are absorbing gases from the atmosphere, so the ratio of carbon-14 to carbon-12 in the plants is the same as the ratio in me. I say this, something that I think is really cool. Okay, it's not cool to take synthetic testosterone, right, to get better at sports. But the test for it comes from testing the ratio of carbon-14 or carbon-13 to carbon-12 in the atoms in the athlete's body. Because most of the food we eat is raised in a climate that is one temperature. They make the synthetic testosterone from soybeans, which are raised in a different climate, has a slightly different ratio. And so if your body has the ratio off, they say, aha, you have synthetic. Problem is, if you're a vegetarian and eat a lot of soybeans, you would be more likely for them to say you're cheating. But they actually take the ratio of isotopes there. Back to radiometric dating. So they measure the ratio of carbon-14 to carbon-12 in something that used to be alive, but is now dead, and they compare it to what's in the atmosphere. And if you have half the ratio, then they say that must be 1 half-life. And so 1 half-life for carbon-14, 5,730 years. So it must have been 5,730 years since it died. What's an inherent problem with what I just described?
The ratio would be different back then?
Yeah, the ratio could have been different back there. What if it wasn't the same 5,730 years ago that it is today? And so scientists understand. Scientists aren't idiots, right? They don't say, who cares? They take things that they can actually date, like archaeological things that people wrote about. You find an artifact that's clearly from that time, and you measure what the ratio is now, and then you calculate back what it must have been in the atmosphere at that time. Or you can use things like tree rings. A tree, when you have the wet season, it grows faster. When you have the dry season, it grows more slowly, and it makes a difference in the color of the ring. So you can look at those rings and you can count years. And so they can use those. So they calibrated the carbon-14 to carbon-12 ratio in the atmosphere to make it so they can actually get a reasonable time. They're not assuming it's been constant for all time. So you'll hear a lot of, remember, I am a creationist. I'm not bashing on creationists, but you'll hear a lot of creationists who don't understand this and say, but how do we know the ratio has always been the same? The answer is we know it hasn't been the same. And in fact, within a year of when I was born, the ratio changed by a factor of, doubled. Why did it double? Volcanic eruption? Right? Things that happen that change our atmosphere can make a big difference. So that's why they have to go and do the calibrations. Okay, so this here is an example of transmutation because it changed from nitrogen to carbon. And it created a radioactive carbon, one that's going to decay over time and become carbon-12 eventually. No, actually it becomes nitrogen again. Excuse me. Here's another example. This is what's going on with uranium. The uranium, the way we think about it is like you have little alpha particles bouncing around inside the nucleus. Every time it gets to the edge of the nucleus, there is a certain percentage chance that it'll come out. Eventually it does, and so you just have, bloop, it kicked out that helium nucleus. And once again, this helium nucleus has no electrons. The thorium nucleus has 2 extra electrons, but those are going to balance out quickly. So that's what's happening with an alpha emission. Now the beta emission, good. We do have the beta emission. Well, that's not a beta emission. The beta emission is not shown here. Carbon. That's the actual equation for the beta emission that occurs with carbon-14. It kicks out an electron from the nucleus that was never there to begin with, and the neutron converts to a proton, making it back to a nitrogen-14. But it also produces another little particle there we call the electron antineutrino. They didn't show the equation because it's a little more confusing. Notice the total number of things in the nucleus didn't change. Oh, wait, wrong. I was pointing to the wrong one. But the atomic number did change by 1. It increased. Gamma emission, finally, is the one that has no change in the nucleus that we can see. What's happened is the nucleus is just rearranged to a lower energy state and given off a photon. So gamma emission, there's nothing to see as far as a change in the nucleus. It's only radiation coming out. So how do you show an equation for gamma radiation? A equals A plus gamma. Right, it's a pretty lame-looking equation. Ernest Rutherford, and now somebody put this in a long time ago when I hadn't talked about it. Make sure when you put your potential test questions, you put in things that I talked about in class. Ernest Rutherford is not only famous for the gold foil experiment, but also for being the first one to actually transmute an element, to make something change from one type of element to another. And so the example shown here is a helium bombarding a nitrogen. You put in 2 protons and 2 neutrons. It's not stable. It decays and gives you an oxygen and a hydrogen. But you've changed it fundamentally. That was Rutherford's first thing, I think. Yeah, that was Rutherford's. And notice it says everything from 93 to 118 on that chart is man-made. They're man-made by bombardment like this. Okay. When an element ejects a beta particle, what happens to the number of protons in the nucleus? Just to answer out loud, obviously. it turns out both of these are correct. I only mentioned, not that one. I only mentioned this one. I only mentioned that you convert a neutron into a proton and eject an electron, but you also have beta plus emission, which is just the reverse, where a proton emits a positron and is converted into a neutron. So it occurs both ways. So both of those answers are correct, but we'd only talked about one of them. What causes the nucleus to change the atomic number by 2? Which kind of decay? What has 2 protons? What does? Helium, or the alpha. So alpha decay reduces by 2. Increases by 2 doesn't exist. Okay, here, discussion of radiometric dating. I already taught this. Got the wrong number there, my bad. Notice it says the method is not exact due to fluctuations in the Earth's carbon-14 production. In my other class, I use the example of Ötzi, the Iceman. You guys may or may not recall, because I think it was about the time you were born, that they discovered a human remains that had been frozen in an iceberg in Germany, like the Ötzi Valley or something like that. And so everybody's excited because this was like, a dude from caveman times or something. And they evaluated him and they did radiometric dating. And when you do radiometric dating, you actually get 3 possible ages because of the fluctuations in the carbon-14 in the atmosphere. And so they say like it's 30% that he's this old, 40% that he's this old, and 40% that he's this old. They're reasonably close, but the scientists are very careful with mapping how much carbon-14 in the atmosphere there has been in the past so that they can be more correct, even if they know we have these different times and I can only tell you percentages of the age based on the analysis. But carbon-14 dating only works for things that used to be living, for things like animals or plants. It doesn't work for rocks. And carbon-14 dating, you can only use it out to about 10 half-lives because you start with very little carbon-14. After 10 half-lives, you divide by 2 10 times, you have a little less than 1/1000th of what you started with. By that point, you have no carbon-14 left. So carbon-14 dating can only date out to about 50,000 years. So how do you date out longer than that, and how do you date things that were never living? You have to use something else. So here are some common dating materials. Uranium-238, it has a half-life of 4.47 billion years. Now, it's believed the age of the Earth is around 5 billion years, 4.7 billion years. So the Earth is about 1 uranium-238 half-life old. If the Earth is about 1 uranium-238 half-life old, how much of the original uranium-238 remains now? About half. Now, there's also uranium-235, another isotope, different isotope. It's still uranium, but it has a different number of neutrons. But uranium-235 has a half-life of 710 million years. So we're about 7 half-lives of uranium-235. So how much uranium-235 should exist after about 7 half-lives? Give you a clue. 2 raised to the 7th power is 128. 1/128th of what we started with. So there's about 1/128th of uranium-235 compared to about half of uranium-238. Hence, what do you suppose we have a lot of? Uranium-238 or 235? We have a lot of 238. 235 is rare. But if you want to make a bomb, you have to have uranium-235. And so that's why they have enriched uranium. Enriched uranium is where they've taken naturally occurring uranium and they've put it into a slurry, basically a fluid, and they centrifuged it and collected the uranium-235 so that they have a much higher percentage uranium-235 that they can use to make a bomb or a nuclear power plant. Now, you can make nuclear power plants breeder reactor stuff. There's a lot of options, but 235 is the optimal material. Other things that are commonly used, rubidium strontium decay, potassium argon decay. That one's especially useful because argon is a noble gas. So if you have a hot sample of rock, that's molten rock, it should drive out most of the gases. So you should start with no argon 40. So when it decays, in theory, all of the argon 40 you have in the rock came from the decay of potassium 40. Of course, just like with carbon 14 dating, we know that in theory is not practice. Some will be lost. Some may have been retained when it was molten. And so they have other checks for that. But all of these are methods used to date old material. One last thing, because I'm talking about this and you'll hear it over and over. Has anyone ever heard of index fossils?
Yes, but I don't know what it is.
Yes, but I don't know what it is. Good answer. Well, when you're looking at old things, like you're looking at the geologic column, you're like, oh, look, here we have, Archaeopteryx, the proposed link between reptiles and birds. How do we know the age of the Archaeopteryx? It is something that was living, right? But if it was living more than 50,000 years ago, we can't use carbon-14 dating. And what if we can't find the right rocks around it? Well, they have fossils that are only found with certain ages. Every time they find a fossil of this type, it always turns out it's in rock that's a certain age. And so they take those fossils and say, this fossil is an indicator fossil. If I find it somewhere, since we only find it at this age, then the reason I'm looking at it must be that old. And so some people get really bent out of shape because they will date rocks by looking at the fossils and date fossils by looking at the rocks. And they say, it's just circular, you don't have any basis. The basis starts with using radiometric dating to then get the age for the fossils that they're using for indicators. I want people who are creationists to understand the arguments and not put up bad ones that then get slapped down and make them look silly. Okay, nuclear fission. The thing that makes atomic bombs go boom or nuclear power plants. It's really important. In science, we can use science for good or for bad. I hope we can all agree that atomic bombs are bad. But using nuclear power, that's good. There is less pollution of the atmosphere, less radioactive emissions from a nuclear power plant than there is from burning fossil fuels. Right? The fossil fuels have radioactive materials in them. You burn it and you release those radioactive materials into the atmosphere. With the nuclear power plant, everything is contained within and you don't release any radioactive materials until you have to go dispose of your waste, which is its own problem. So you can use it for good or for bad. And I don't know how many people have been to like Hiroshima, but you look around there and you see the museum and it's definitely for bad, right? There's no argument. When you see one of the things they have in that museum that really impacted me was the bricks outside of a bank. And on those bricks, you could see the shadow of a person because there was a person sitting there waiting for the bank to open. When the bomb detonated, you had an enormous number of neutrons that went flying out. And those neutrons, when they hit the person, a lot of them were absorbed by the person and didn't hit the brick. When they hit the brick, they actually bleached the brick so it got lighter. And so you see shadow of the person because of all the neutrons they absorbed that then didn't lighten the brick behind them. You think about that, and that's kind of scary. How come the queen changed from one person to the other? Did you answer a question right? All right, so nuclear fission is an interesting beast. You have uranium-235, half-life we saw of 710 million years. So you have a sample of uranium-235, it's not going boom. It's very slowly decaying. But if you have a neutron hit a uranium-235 nucleus, if the neutron's going slow it can be absorbed by the nucleus. If it's going fast, it just goes right through and there's no problems. But if it's going slow, it'll be absorbed by the nucleus, but that's unstable and the nucleus breaks in half. Not necessarily two equal halves. The actual elements, this shows krypton and barium. That's what we always show in physics class. Those are the most common, but there's a lot of different variations. And it gives off more neutrons. Now here's the thing about this. It took one neutron to get it started. You know, just like it only takes a spark. Yeah, exactly. How many neutrons came out after it split up? 3. Which means one nuclear fission reaction takes one neutron to start, but how many can it start after it? It can start 3 more. Which means if I have one neutron coming in, then I have 3, then I have 9, then I have, and I can't do the math anymore in my head. But the number of reactions increases exponentially. When that happens in very short time, you have a very large number of reactions and you have a bomb because you have an enormous release of energy. So that's how a nuclear bomb works. So why doesn't it always happen? Anytime you have uranium-235, because those neutrons have to be slowed down. So to make a bomb, you need something that's going to slow down the neutrons so that they can interact. And so you have geometry of how you make the bomb. In a nuclear power plant, you put in something we call a moderator that slows down the neutrons to make them so they're more likely to react. Then you put in a control rod that absorbs the neutrons so that they won't go on to react. Because in a power plant, you want your temperature to remain constant. If your temperature remains constant, what would that suggest about the rate of the reaction? Constant, which means we need to cut that from 3 neutrons that can contribute to just 1. So we have to absorb 2 out of every 3 to make it run at what we call critical, where it's at a constant rate. So here is a picture just illustrating this is how the bomb works. You have one neutron starts it all, and all of these neutrons and all of the other fission reactions occurred because of the one that started it. That's bad, right? Critical mass is when you have enough mass that neutrons are going to slow down by collisions within the material until they slow down enough to be absorbed. So if you get a big enough piece of uranium, it can be a bomb. So one way of making a nuclear fission bomb is simply by taking 2 chunks, each one that's about 3/4 of the mass necessary for it to actually blow up, and you keep them separated. Maybe put some lead in between to stop the particles from getting through. Then when you want to go boom, remove the separator, use a little conventional explosion to push the 2 together, and you have a supercritical mass, and it goes boom. Not very technologically savvy to build that, right? So why do they spend all this time and energy building these bombs? To increase the damage it does, to make it a more efficient bomb, make it release more energy. Another design they use is a symmetric implosion, where you have a bunch of pieces that would form a sphere if you put them all together, but they're all out here separated. And then you have an explosion that pushes them all together to make a sphere. That allows you to have more mass in the final case, and thus a bigger bomb. What are we not going to do in this class? Make bombs.
Are you sure?
100% positive. Okay. What's the difference between these 3 different uranium nuclei? They're different isotopes. What does it mean if they're different isotopes?
It means they have the same number of, they have the same tons with different neutrons. Yeah?
Now I want to point something out. Iso means same. P here in isotopes. What do you suppose isotones means? Means the same neutrons, right? You just replace that N with a P, and it's the same number of neutrons, but different number of protons. Where is that useful? Not so much, because when you change the number of protons, you change the chemical properties, and And that's what we're usually concerned about. Okay, this is the final thing. Everybody knows that Einstein is famous for his E equals mc squared equation. Well, most people don't understand it. They've heard of it, but don't understand it. E is the rest energy. We never talked about rest energy before. What kind of energies did we talk about? Potential and kinetic. This rest energy is a different kind of energy. We will talk very soon about chemical potential energy, but that's a type of potential. Rest energy is energy something has because it exists. Mass, according to Einstein, according to this very equation, is just a form of energy. And so if something has more mass, it has more energy. So you could look at me and say, that Webb kid, he's full of energy, right? Because there's a lot of mass in me. That's a physics understanding. That's what that equation means. Now, why is that in any way beneficial or useful to us? Because when we have a reaction like that nuclear fission we were just looking at, the actual mass of the particle you start with and the particles you end with, they're not the same. You end with a lower mass. A lower mass is you have less energy in mass. Where did that energy go? That's the energy that was released. And so we can calculate how much energy is released by measuring the mass we started with and the mass we ended with. Take the drop in mass and multiply that by c squared, and that tells us the energy released. So I'm going to go, this is the equation, right? Energy release is delta mc squared. This graph here, this is a graph of the mass per nucleon. A nucleon is something in the nucleus, so protons and neutrons. Mass per nucleon versus atomic number. And what's really key is that it's a minimum at iron. That means a proton in iron has less mass than a proton in hydrogen. If the proton has less mass, the energy had to go somewhere. And so if you take protons and you combine them to make iron, it's going to release a lot of energy. Hence, in very massive stars, you can have nuclear fusion combining nuclei together all the way up to producing iron, and it keeps releasing energy. But it won't release energy if you go any bigger than iron, because then the mass is going back up. On the other hand, nuclear fission, breaking things into smaller pieces, will release energy if you go toward iron. The biggest energy release per nucleon is going to be when you have the biggest mass difference. So, as you can see, if I could somehow move from here to here, that's a lot more energy per nucleon released than if I go from here to here. What's going on if I move from here to here? What type of nuclear situation is that? Getting to bigger atomic number. It's fusion. Fusion is putting things together so you have a bigger atomic number. So fusion will release a lot more energy. Hence, if we can manage a controlled fusion of hydrogen to helium, that will give us a lot more energy per fuel than we can ever get from nuclear fission. But we can't control that. The sun controls it. The sun is right now fusing hydrogen into helium. That's how it operates. But we can't control it and maintain it. So what we're doing in our nuclear power plants is fission, where we have something like uranium breaking into smaller pieces, releasing energy. In which one of these does a proton have the most mass? Which one? I still didn't hear you. Uranium? It is not uranium. What'd you say?
Aren't they all the same?
They're not all the same. That's what this graph was saying.
Wow.
The mass, mass per nucleon, so I can say mass per proton. The mass per proton is the lowest right here. So iron, the proton has the least mass. For what element does it have the greatest mass? Which one's going to be the highest? Okay.
Hydrogen.
Hydrogen is at this edge, so it's going to be hydrogen.
Oh, really?
So hydrogen, you have the greatest mass for the proton. For iron, you have the lowest. Lead and uranium, it's going back up, but it doesn't get anywhere near as high as it was for hydrogen. The rest of these pictures are all fundamentally the same thing, showing you what's happening with fusion and fission. And it's time to start the lab.